Hey, welcome back. Today we're going to be talking about what are standing waves, why standing waves happen, and how to solve problems associated with them. So take a look at two of my students here creating a standing wave with a slinky and what they're doing. And first of all, I could say what a standing wave is it's a wave that appears to not move. And the reasons why that a standing wave have to do with two concepts that you may have seen already in your physics course. So that would be superposition and reflection of waves off of boundaries. But I will explain, so let's go ahead and get to it. Okay, and so I do want to talk about two reasons why standing waves actually happen. And one of those reasons is because of superposition. That's when two waves interact with each other, and the crest of one wave will add with the crest of another wave, and the crest of one wave will sort of fill in the trough of another wave, so you have either constructive or destructive interference. You can see that the red wave here is based on the blue and the green waves being added together. And I've done a screencast on that. If you want a little more background, I'll put a link to that in the upper right about now. But I do want to talk about another reason why standing waves happen, and that's because of how waves will reflect from different ends. I want you to take a look at what's happening here. So when the wave is reflected, it's not going to be inverted. That means it's not going to be flipped upside down when we have something like this. If you have a free end, if this is free to slide up and down, then there's no resultant force on the medium in the y-axis. There's a resultant force, there's a pushback force in the x-axis, which is what causes the wave to move in the backwards direction here when you have free ends. But it's very different when you have a wave traveling on a medium heading towards a fixed end of the medium. So let's see what happens. Let's see, you have something like a wave traveling through, a wave pulse. What happens is, if we take a little bit more of a closer look, the wave pulse is going to pull against the end of the medium itself, and the medium itself is going to pull back. So the wave is actually pulling up. This is more of like the action, and then this is the reaction from the wall. This is the force on the wave from the wall. And as a result, you have a value like this, where the wave is actually going to become inverted as it flips. So that's one of the reasons that standing waves happen is if you have like two ends of a guitar string or something like that, you can have constructive and destructive interferences happening when these waves bounce back and forth from one fixed end to another fixed end. And we have seen that with the animation that you saw previously. Alright, and so let me show you an example problem and how you would approach it for standing waves, comparing different standing waves. Let's say, for instance, we knew this length right here, that we measured this when we took this video, and it was 2.2 meters. We can think of that as an equivalency. And it's been a while, but you can think of this as an equivalency where you say 1 lambda, one wavelength, is equal to 2.2 meters. Now we can convert that into a fraction that's equal to 1. Let me remind you of how you would do this. If you divided both sides of the equation by 1 over lambda, because you wanted 1 over lambda on the bottom, what would that do? Well, that would cancel out this fraction on the left, and that would be equivalent to 1. So now we know we can say we have a fraction equivalent to 1 of 2.2 meters over 1 lambda. Or we could do it the other way. We could start with this same equivalency. 1 lambda is equal to 2.2 meters. If we wanted to have 2.2 meters on the bottom in the denominator, then we would have something like this. And these will cancel. You'll be left with 1. So let me show you how to apply this for a ranking or a comparison style problem. So if we take a look at this, for A, we need to figure out how many wavelengths we have. So if we take a look at this, we've got a wavelength of 2.5. This whole thing is L, so the whole distance is L. So first of all, we could say L is equal to 25 centimeters. And we could also say, well, what is that L in terms of wavelengths? Well, that actually is going to be 2.5. We've got one full wavelength here, one full wavelength here, and half a wavelength here. So we could say 2.5 lambda for A is equal to 25 centimeters. Now we want to convert. The question is, what is 1 lambda equal to. So we could say, well, 1 lambda times, and we're going to multiply by a fraction. This is like dimensional analysis. Down below here, you want to get a lambda to cancel out. And if I'm looking at this equivalency that I'll put in brackets right here, we're going to have the 2.5 is going to go with the lambda, and the 25 centimeters is going to go up top in the numerator. What does that leave us? That leaves us 10 centimeters. In other words, one wavelength for A is equal to 10 centimeters. Alright, we're going to do something similar for the other ones. Let's start with B. So B, we would say length is equal to 28 centimeters. Now we need to figure out how many wavelengths we have. We've got 1 full wavelength, 2, 3.5. So we're going to say 3.5 wavelengths is equal to 28 centimeters for B. And so the question is, what would 1 wavelength be? So 1 wavelength, and we're going to do a conversion here. Remember, we need wavelengths on the bottom, and we've got 28 up top. And what does that turn out to be? That's going to be 8 centimeters over here. Now let's do C and D, and then we can rank them. And the question is, how many wavelengths do we have here? Well, we've got 2 full wavelengths. So we could say 2 lambda is equal to 20 centimeters. Okay, and so the question is, what would 1 lambda be? And we're going to multiply it by a fraction here. We need lambdas on the bottom, so 2 lambda over here, 20 centimeters goes up top. And so we're left with 10 centimeters. In other words, 1 lambda for C is equal to 10 centimeters. Last one, let's do together. We take a look at D, and so the question we could ask is, how much is 1 lambda for D? So we need to have our lambdas down below, and our centimeters are going to be up top. Lambdas are not units here. They're more of a concept, but they're helping us to visually understand where to put these numbers. The 1.5 goes with that lambda, and the 30 goes with the centimeters, and as a result, you're going to end up with 20 centimeters. So 1 wavelength for D is equal to 20 centimeters. So how do we go about ranking these? Just go from greatest to least. So we end up with D being the greatest, A being next, which is equal to C, which is greater than B. Notice that the amplitudes play no role in this in terms of the ranking of the wavelengths. Hopefully this has been helpful. I've done screencasts on an entire year of physics and most of the concepts for AP Physics C mechanics as well. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.